bit of physical understanding, we will try to simplify the equation of motion based on the derivations that we have made till now. So, the first simplification is we will put back the tau ij expression in the equation of motion. So, if we put back the tau ij expression in the equation of motion, then it will boil down to okay. So, we have done nothing special, we have just substituted the tau ij in the equation of motion. So, we can make certain simplifications. Let us say we are bothered about the first term. See, delta ij equal to 1 when j equal to I. So, the first term will become, so you replace the index j here with I, then only this is 1. Then next, for the next term also it is the same. For this term replace the index j with I because of the multiplication with delta ij. For the term in the last bracket, you have basically two terms. The first term is this and the next term is okay. See, when you have a second derivative and you write in a index notation, you have to be very careful. Say you are writing this term, okay. So, if you write it in an index notation, say this is ui. So, if you write it in this way, it will give you a false impression that the index I is only once, but fundamentally it is like this one. So, actually it is a repeated index. So, if you may always use this notation of del square, but you have to be careful that that is just a notation, it is basically a first order derivative repeated once. So, you actually have a repeated index, this will not give an appearance that it is a repeated index. So, here that is why we have just kept it the form which is like a first order derivative operating on another first order derivative, so that the sense of the repeated index is preserved. Now, if you see that this is a okay, first of all let us say that we are dealing with constant properties. So, if you are dealing with constant properties, maybe the mu one you can take out of the derivatives. Now, if you take the mu out of the derivative, see at the end here, say for this term you take mu out of the derivative, if it is a constant, it may not be an absolute constant, mu may be function of time, say as an example, but important thing is it is position independent, because these are derivatives with respect to position, and for a homogeneous fluid it has to be like that. So, our earlier assumption of homogeneous fluid is not very inconsistent with this one. Now, then it is possible to switch over with these derivatives, that is you may have I here and you may have j here. Why? Because it is a continuity with of the partial derivative, second order partial derivative. So if the second order partial derivative is continuous, say you have this, you can write as this one, if the second order partial derivative is continuous. So you may either do derivative with respect to x first and then y, or with respect to y first and then x, still they will give you the same result if it is a continuous second order partial derivative. So here we are assuming that it is a continuous second order partial derivative. So there is no discontinuity that we are assuming, and in a continuum hypothesis that is something what we should presume anyway. So then what does this term become? Maybe again you may put mu back inside, because mu is a constant, so you can play with it either inside or outside. So then it will become right, okay. This, is it possible to write it in this way, mu into, you replace j with k, yes or no? Yes, because this j is a dummy index, so there is a summation over that from 1 to 3. So basically you are substituting this first 1, 2 and 3 and adding, it does not matter what name you give it to this j, k, l, m, whatever, right. So this is called as a dummy index. That means what you get in the right hand side, let us therefore write the right hand side. So this is equal to minus so you may club two terms, which terms? You may club one term like this with another term like this, right. So you can write this into lambda plus mu and then okay. So when we have come to this stage, let us recall what are the assumptions which are valid, which are there for which it is valid. What are the assumptions? So first we started with a stationary reference frame, then the next assumptions, Newtonian fluid and homogeneous isotropic fluid. Stokes hypothesis not yet imposed, right. Before imposing the Stokes hypothesis, let us make another simplification by now looking into the number of equations and number of unknowns. See, whenever we are solving a problem mathematically, we are always bothered about the number of equations and number of unknowns, which somehow we try to match, and when we try to match, we have an important understanding that number of independent equations should be same as the number of unknowns, so that you can solve for the unknowns in principle from the equations. It is not so important first to know how you solve, but at least it should be a well posed system which is solvable. So to understand that, if you see here now, let us consider a Cartesian system. So when you are writing ui, see I is a free index, so you have 3 equations for I equal to 1, I equal to 2 and I equal to 3, which are like linear momentum conservations along x1, x2, x3 or x, y, z, 3 mutually orthogonal coordinate axes. The number of the unknowns you have u1, u2, u3, which is like u, v, w in the other notation, and pressure. So you have a fourth unknown, and that is one of the big troubles, you do not have an explicit governing equation for pressure, and to have that we only have a resort that we have one equation extra that we can always use, that is a continuity equation, but that does not explicitly contain pressure, but still it contains the unknowns u1, u2 and u3. So at least if you couple these with the continuity equation, that will close your number of equations and number of unknowns, they will match. So we are always going to use these equations in conjunction with the continuity equation. that must be valid. So let us now try to simplify this equation by utilizing the continuity equation. Till now we have not simplified it using the continuity equation. So this form of the equation is known as the conservative form of the equation, because see we have not disturbed the form which has come from the control volume conservation. So we started with the control volume conservation by using the Reynolds transport theorem, and we just converted it to its corresponding differential form, but we have not disturbed the form. So this still is something which you can recollect that has come from a conservation principle directly. We have not simplified it further, but now utilizing the continuity equation we will simplify this further in the left hand side, and that will bring us to some form known as non-conservative form. So to do that, let us write the left hand side. So we will use the product rule of the derivatives and simplify it. So you can write this as ui that is the first term, then for the next term you club up rho uj as one term and ui as another term and use the product rule of the derivatives. So you have okay. Now let us combine these two terms where you have ui as common. So if you combine these two terms you have ui and then let us write the remaining terms. Okay. Clearly what we can see that the first term in the square bracket is identical equal to 0 by the continuity equation. So this is 0, exactly equal to 0 by the continuity equation. Okay. So you come up with a simplified form of the left hand side which is nothing but just the second term which is remaining. And this term you can write in terms of the total derivative capital D dt of what ui by the notation of capital D dt that we had discussed earlier. So the equation of motion may be simplified now to this form. What is that form? So we just change the left hand side with this simplification. Which is as good as okay. Sometimes when this form is used it gives an illusion. What is that illusion? As if it is valid for a constant density fluid. So this is where knowing the derivations are important. If you do not go through the derivations and just look into it, use of common sense might lead you to a conclusion that as if rho is a constant, that is why it is out of the derivatives, and intuition wise that is correct if you do not know the derivations, but if you know the derivations you will realize that this rho has come out not because that it is a constant, it may still be a variable, it has come out by use of the continuity equation and most general form of the continuity equation, not for rho equal to constant. Okay. So then is this valid for compressible flow? Yes, it is very much valid for compressible flow, because we have not simplified any further by using the concept of incompressible flow or the consideration for incompressible flow. So the assumptions over which these are valid are the same as the assumptions for which this was valid in its previous form, that is the conservative form. So these are just two different forms, and one may interchange one form with the other. Usually we will see that, see these equations are not very straightforward. See, these equations are some of the very complicated equations to solve with in applied physics and applied mathematics. Why? See, these are coupled non-linear partial differential equations. So, these are not linear partial differential equations, these are coupled because you have these, at least these equations plus the continuity equation. So, at least the 4 equations which are there, which are coupled with each other, because each equation contains some of the terms which are related to the other. Highly nonlinear, pressure is residing on some of the equations, but you do not have separate governing equations for pressure. So, these are some of the challenging aspects of these equations. So, in most practical cases you cannot solve these equations analytically, and you have to use computations, numerical computations to solve these equations, and that leads to an entire specialized branch of fluid mechanics known as computational fluid dynamics, or CFD. So, that is, CFD is basically all about the numerical solutions of the partial differential equations of like momentum conservation, continuity, and then these may be again coupled with heat transfer, mass transfer if those are also involved. So, all these coupled partial differential equations. The other transport equations, that is the heat transfer equation or the mass transfer equation, at least they are not nonlinear, but the momentum equations, they are nonlinear, because you have terms like, if you look into this term, like look into uj into the partial derivative of ui with respect to xj. So, this is actually the nonlinear term. So, if somehow this term is not there, we will see under what conditions this term is not there, then it simplifies the situation considerably, and there are certain special cases in which analytical solutions are available, and we will work out some of those analytical solutions as a part of this course, which are known as like exact solutions of the equations of motion. Now, next thing is that we have not used the Stokes hypothesis, and let us use the Stokes hypothesis at this stage. So, you substitute lambda is equal to minus 2/3 mu. So, then lambda plus mu is known as bulk viscosity of a fluid, it is just a name. So, the bulk viscosity, then it will become mu by 3. So, this term will become mu by 3. Okay. So, we have utilized now the Stokes hypothesis in the equations of motion. So, the corresponding equation of motion will now become, in place of this we will substitute the Stokes hypothesis. Let us write it a bit cleanly. So, mu by 3. So, we started with the Navier's equation of equilibrium, which is basically this one, substituted the constitutive form of tau ij for a Newtonian fluid for homogeneous and isotropic fluid material, and then now we have substituted Stokes hypothesis, and then this is known as Navier-Stokes equation. So, Navier's equation for a Newtonian fluid plus homogeneous isotropic special type of Newtonian fluid, and most importantly a fluid that obeys Stokes hypothesis, that is known as a Stokesian fluid. So, just like a fluid that obeys Newton's law of viscosity is known as a Newtonian fluid, a fluid that obeys Stokes hypothesis is known as a Stokesian fluid. So, the fluid is a very special fluid for which we are writing this equation, Newtonian and Stokesian fluid, and with homogeneous and isotropic fluid properties. So, that is known as Navier-Stokes equation. When you have, so this form of the Navier-Stokes equation is valid both for compressible as well as incompressible flow. When you come down to the case of an incompressible flow, as we have discussed, that it really does not matter whether Stokes hypothesis is there or not, whether it is violated or not. So, for incompressible flow we can clearly see that this term is not there, because this is 0 for incompressible flow. Because that is the rate of volumetric deformation. The most fundamental definition of incompressible flow is that you have 0 rate of volumetric deformation. So, when you have the incompressible flow, it does not matter whether lambda is equal to minus 2/3 mu, this term is identically equal to 0. So then if you write the Navier-Stokes equation for incompressible flow, which we will be dealing with in our subsequent exercises. So that will be rho okay. So although Navier-Stokes equation, it actually does not require Stokes hypothesis, it is just good enough to have a Newtonian fluid with homogeneous and isotropic fluid properties, and we will be often using this form of equation for our calculations or for the exact solutions that we will be deriving in the subsequent classes. So it is possible to write these in a vector form also. So if you want to write these in a vector form, or let us first write it in a well known UVW component form. So if you want to write it in a UVW component form, you have so this is right. If you want to write by using the notation u1 equal to u, u2 equal to v and u3 equal to w, and write it in an expanded form. This expanded form is often useful if you are solving it analytically, because you are interested to get a full feel of the terms. So if you see that, what do these terms indicate? Left hand side is like what? When you are writing rho into capital D dt of ui. So rho is mass per unit volume and this is acceleration of flow. So this is like mass into acceleration of flow per unit volume, and by Newton's second law the right hand side therefore should be force per unit volume. So so it is just like a Newton's second law of motion written for fluids in an Eulerian frame, nothing more than that. So the right hand side, what are the forces which are there? This is a force due to pressure gradient, this is a force because of viscous effects, and this is a body force. If so the body force may be anything, like it may be because of gravity or whatever, but it is important to recognize that it is something which is a very general force that we have kept here. So there may be effects of electrical field, magnetic field, or many other forces may influence the fluid flow, and all those extra effects will be appearing in this form of the body force. So what we say at the end is that if you have the Navier-Stokes equations, the Navier-Stokes equation should be coupled with the continuity equation. So this we say that this is the x component of the momentum conservation. Similarly you can write the y component and the z component, so y z component and the continuity equation. So that will be the coupled equations which will involve your all equations and unknowns, and we should be in a position to simplify those for specific problems to solve the equations to get the velocity and the pressure field. So that will be our objective from the next class onwards. We have to keep one thing in mind, that these Navier-Stokes equations whatever we have derived here, see there are certain things which we tend to take as rituals. So Navier-Stokes equations in fluid mechanics have been taken as rituals for long, and it was thought that these equations are giving the correct physical meaning for almost all cases. But there are certain cases where it was found that this equation is not giving the right picture, although continuum hypothesis is not totally violated, still it is not giving a very consistent picture. I will give you one or two very simple examples. Let us say that you have a molecule, gas molecule, which is subjected to a very high density or temperature gradient. So, when it is subjected to a very high temperature gradient, because of the temperature gradient the gas molecule may start moving, and this is sort of called as self diffusion. So, it moves within its own medium because of strong local gradients of temperature or density. Now, that is nowhere manifested in these equations. So, if you just use these equations you will get a 0 velocity, because you do not have any term in this equation which is representing a sort of local density or local temperature gradient driven motion or flow, and this is an example which is known as thermophoresis. So, or sometimes it is called as diffusophoresis because of the self diffusion. So, these types of motions which are achievable in highly rarefied systems, this is not manifested in these equations. So, what we try to do is that we try to correct the Navier-Stokes equations and try to incorporate those terms, so extra terms, so that it may be able to physically incorporate the effects of those like thermophoresis, diffusophoresis types of motion, and that is how we extended the Navier-Stokes equation. So, this beyond the scope of this study or this class to discuss that how we did it and what are the important remarks, but only one observation, that is one of the thought processes that I would like to share with you is that whatever you are learning, see at most times as teachers we tend to believe or we tend to tell you that as if we are gods, we know everything and it is your responsibility to like digest that, but most of the things actually we do not know, and I think our greatest objective should be to tell you that what we do not know rather than what we know, but first we tell you what we know because it is easier for you to digest that. So, the Navier-Stokes equation in the very classical form was something which has a mystery, which did not contain something. We tried to correct that. I am not saying that we corrected it fully because we could do it only for ideal gases, but at least it was an extended form. So, the long history of how the Navier-Stokes equations were there, at least over the last 2-3 years we could change it and extend it for more general types of flows. So, with this we stop this lecture today and we will continue in the next class. Thank you.